hope we are. I am still playing with this a little bit, so I get an indication. It looks like things are working all right. How are y'all doing tonight? All right. So, all right. Hey, Gus is here. Good to see ya. All right, hold up. Let me get a couple of things going here. Nate, good to see you. All right, thanks, Jack. So everybody, the Jack, who is usually moderating for us, is because it's a Twitch stream. He's not as vocal as usual, but how do you even say that, Jack? I know it's your Walker Jack backwards, but it looks like it's Cadraclaw or Cadraclaw. The sword icon means that he's a moderator. So, you got any questions for Jack? You can talk to him there. Hey, Alejandro, good to see you. All right, so yeah, welcome to Twitch. I'm excited to be on this platform. Been looking forward to this for a little while now, hoping that we'll have a little bit more interactivity here. So, I'll try to keep an eye on the Twitch chat, which is to my left over here, so I keep looking over there. And so be sure to chime in with anything and everything. Jack's got my ear as well in case there's something that I miss, so we'll just kind of keep this interactive. So for anybody who hasn't been hanging out with us, we just wrapped up a series on the Ccent. So ICND 1, which is Cisco's current entry-level exam. And so I just want to make sure, I want to take a few minutes here just, for, again, get us all on the same page as far as what Cisco is doing with certifications. And February 24th is a big day, and that's coming up here. So let me see here. Yep, that looks like it's working. So February 24th, 2020, what's happening on this day? So what's happening first and foremost is the Ccent exam is going away. It will be retired, not just the exam, but the certification as a whole. So anybody who has a Ccent on February 24th is going to lose their Ccent. And that is a little bit unfortunate, not going to lie. I wish they hadn't done that, but I also understand why they're doing it. I'm very excited overall for all the transformation that this program is going through, especially at the CCNP and CCIE level. That really excites me. But at the same time, what they're doing here at the entry level is to simplify it. Because if anybody's been looking into certifications, it's, okay, yeah, I start with the Ccent, but I've got CCNA, route switch, and security, and data center, and voice, and wireless, and cyber ops, and industrial, and all of these different CCNAs, and we're bringing this down. So all of the CCNAs, so many CCNAs is going to be reduced to a single CCNA. So effectively, this does become our entry-level exam, but keep in mind one other thing. Cisco has these certifications called the CCT, Cisco Certified Technician. There's a routing and switching version, and there's a data center version. These exams, these certifications have been around for a very long time, since like 2011, but nobody really takes them, and because the Ccent is really where Cisco wants entry-level folks going. And because of that, as far as entry-level is concerned, we would always skip over the CCT. Well, now that there's no Ccent, there might be some interest in the CCT. So we're going to keep that in the back of our heads, that these two CCT certifications do exist. But for all intents and purposes, CCNA is where we want to land. It's going to be where our entry level is going to be. And for years and years, that was the entry level. Cisco came out with the Ccent, and now they're retiring the Ccent. So why did we just wrap up? We just wrapped up Ccent training. Why, knowing all of this, did we just do Ccent training? Well, the reason is because on February 24th, if you have a current CCNA, even though the current CCNA is getting retired, they will update or upgrade you to the newest CCNA. And so if all we do by February, end of day February 23rd, all we have is a Ccent, that's unfortunate. However, if we can maybe this month get the Ccent, and then in the next couple months after that we're able to get the CCNA, then it was all worth it. So call this a last-minute cram session. Every Tuesday night through November, through December, through January, and even for most of February, I want to make this, I'll bring topics to talk about. Like tonight we're going to talk about spanning tree. If you scroll down a little bit below the video here, down here, you'll see the schedule as I'm thinking it's going to be. I'll try to keep that as updated as possible so you can see what's coming. So you can prioritize being here if it's a topic that matters to you, and you can take the night off if it's something that you feel like you've got a handle on. And ideally, by just kind of coming together, we can help you tackle getting the Ccent by February. So right now, Jack is here for, again, Jack is a moderator in here. It's Cadraclaw. So Jack Walker is fantastic community outreach spokesperson for the CBT Nuggets community. I'm going to add some resources down below as well here. Still kind of, this Twitch channel is under construction a little bit, but I want to make sure everybody has the resources. So CBT Nuggets community is a free resource. You don't have to be a subscriber. These Tuesday nights are a free resource. By the way, for those who know Jeremy Chara, he's also on Twitch, and he's doing Thursday and Friday night sessions on CCNA. And so if you can tune into all of these resources that are available to you, hopefully they'll empower you to go get that certification. So if you have any thoughts or questions on certifications, feel free to chime in via the chat. Otherwise, thank you, Jack, for chiming in with the URL for that. I'll get that again put in from a resources perspective. A hyperlink below. That's what I was looking for. So, hey, Nikos, welcome. Good, everybody's here. All right. So, without further ado, let's get to some spanning tree conversation. Spanning tree is so fun. It really is. I like it a lot. But it is a little bit complicated. So, hey, we've graduated. We're no longer talking Ccent. This is CCNA, and CCNA is pretty serious when you get up to this level. They want you to know spanning tree. They want you to know OSPF and a little bit of EIGRP, and they want us to understand more in depth how routing and switching work in general. And so this is kind of a gloves-off type of topic. Spanning tree can make or break a network, and trust me, I've seen it break some networks. I personally broke a network with spanning tree once, so I maintain it was a bug in the iOS, which of course never happens, but I probably wasn't as careful in my junior years as I probably should have been. We'll get to that story eventually here tonight, probably. Remind me if I don't actually tell that. So what's the goal of spanning tree? Well, let's talk about why we need spanning tree. The reason we need spanning tree is because Ethernet as a protocol is pretty bad. I laugh because over the years, Ethernet was the cheap standard. We had token ring as a much more viable option, and Ethernet was just cheaper. Everything was cheaper, and usually the cheap thing wins. VHS won over beta as a standard. I think the only place that didn't hold true was Blu-ray won over HD DVDs. That was the first time where the more expensive technology actually won. More expensive usually means better. But because Ethernet is a bad protocol, we are constantly patching it. And so spanning tree was a patch, and spanning tree is not good enough. So we invented ether channels, and ether channels weren't good enough. And so we invented virtual port channels, and just all kinds of crazy stuff to try to make Ethernet a workable protocol at scale. For the most part, we don't need spanning tree in our homes, but any enterprise network is going to require this. So the problem is Ethernet has this great feature called a broadcast, and the broadcast means if I receive a broadcast, so if I as a switch, bring this down here, there we go. All right, if I as a switch bring a broadcast packet in, my job is to send it out every active interface. I don't care if there's a switch on the other end, or a wireless access point, or a PC, or whatever. I'm going to send it out all of my links. And that does include to the next switch. So we repeat. Broadcast comes in, switch sends it out all of its connections, including the one to the next switch. We repeat again. Broadcast comes in, and we're sending to all of our connections out this switch, including, as we'll notice, and the problem, hence the problem, back to the original switch. Well, technically this was the original switch. I'm the switch who originally sent it to you, but this switch has no way of knowing that this is a packet of the original packet that I sent. And so because of this scenario, if we loop, we are all aware of network loops for the most part. If you've been in IT longer than a few months, you've probably heard this term, network loop or spanning tree loop. This is the scenario. We loop our switches in a circle in some fashion. Sometimes, by the way, oh, you can't see the whiteboard. Oh, thank you. Holy smokes, I've been writing. I got to get used to Twitch. Sorry. There we go. That better? It's not Twitch that I have to get used to. It's the new interface here. So, can somebody tell me, are you seeing this now? Wait for a little bit of. All right, perfect. Thank you, Jack. All right, sorry about that, guys. Hey, you know what? Now this is too bad because look at this. I had all of this written out. I was writing stuff for the Ccent and everything, so I apologize for that. I started off full screen and I forgot that with Twitch, I've got to get used to it being not automatic. All right, technical difficulties. Understood. Okay, so the 30-second version. Originally, I had a broadcast here that came in, and we're talking about how the switch receives that broadcast, sends it out all of its interfaces. So it sends it out all of its interfaces, which of course sends it over here, sends it back up. This is the loop. So a broadcast is going to live forever. And that would be well and good. I mean, maybe we could deal with a little bit of broadcast traffic. But unfortunately, there's a lot of it. Like every time a PC comes online, it's going to send a series of broadcast messages in order to get an IP address. There's a lot of discovery type of protocols that are happening on the network at any time. And so there is a tremendous amount of this broadcast traffic that is happening at any given time. And so as we build this traffic up, what happens is these links fill up. So, we might have a gig link here, and all of a sudden 700 meg of that is just repeated broadcast traffic. The bigger threat, I will tell you, the bigger threat is less the bandwidth and more the CPUs on the switches. Because the CPUs can only handle so much at once, and even though a lot of this is ASIC driven and it's going to hardware switch as much of this as possible, when it comes to broadcasts, we actually do need some CPU intervention, and it's just going to chew up the CPU cycles. As soon as things start overflowing the buffers and we have to deal with all of that, it just becomes a mess. So the bigger threat is that our switches will start shutting down. And I'm not just talking about little rinky-dink switches. I'm talking about the big cores that Cisco or other network vendors make. There's a lot of it just doesn't matter. It doesn't matter how big they are. They all fall down to a broadcast storm. So that's what we call this. Call it a broadcast storm. Broadcasts are going everywhere. Sometimes if you look at a switch and you see all of the lights just like blinking like in sequence with each other, so it's not like a little, normal network traffic is it's all over the place. If they're all just blinking together, that's a bad sign. That usually means that there's a broadcast storm in effect. All right, so looks like we're good with this now. So thanks guys for sticking with me through that. Okay, so this is what spanning tree was designed to fix. Spanning tree, the idea of spanning tree is that we want the network to automatically, we don't even need manual intervention in this, automatically recognize when there's a loop and block it. So maybe we'll say that we're going to block this link right here. And more accurately, from a spanning tree perspective, we would say that this port goes into a blocking state. And yes, that means that the port upstream is not in a blocking state, but I want to get that out of the way because for years I thought, when I was a junior engineer again, I thought that the link was blocked. It's not. It's just one side of the link. So in our situation here again, this drawing's getting a little busy, but once this broadcast, let's say I send a broadcast traffic all the way around, I'll change my color here, purple. So I send a broadcast out this way to the left, it goes up, and yes, that switch is going to send it back down, so it looks like it completes the loop. But because this port right here is in a blocking state, it rejects not only that broadcast message, but it rejects all traffic coming in on that interface. So that's the goal here. We've created what you call a tree. If I were to take this switch here and dangle it, like as if these switches were hanging from string, we'd have a switch up top and we'd have two switches hanging below. And if we had another switch in this, let's say we had a switch down here and it's connected in. And let's say that this is the let's say this is the blocked link down here. Well, now we've got let's see here, 1, 2, 3. Actually, you know what? I'm gonna make a different link. Let's say this one's blocked. So now this switch is hanging off of one of these other ones. But the idea is that you can grab a switch, usually what we call the root switch, and imagine plucking it off of the drawing, holding it up, and the other strings, the other switches hang off as if on strings, and there will be no loop. Even though a network drawing can be more complicated and doesn't ever look that way. But again, we have an actual tree that flows like this. It looks visually like a tree with a root system, so to speak. You can draw the tree two different ways. You can say that this is the top of the tree, but really, if we flip it upside down, now it looks like it's growing up, like almost out of a flower pot. So this is technically the visual picture we want to think about, because again, what we call the base of the tree is going to be the root. And of course, the roots for a tree are all the way at the bottom. All right, so let's get a new drawing pulled up here and start talking about this process. So when we first connect 3 switches to each other, a lot's going to happen. So let's just say that we connect all 3 of these switches at once. Magically, they all connect at the exact same time. And they are all going to start talking to each other in what we call a listening state. Well, it's kind of weird to say that. Do the blocked links still receive Bpdus? That's a little bit of a fun question. First of all, we'll get to Bpdus in a moment, but technically speaking, by vanilla spanning tree protocol perspectives, they will reject Bpdus. Okay, so they don't need to see anything coming from the upstream connection. But Cisco has made some enhancements, and STP enhancements have come out that say, you know what, we really do want to keep receiving those. So we'll talk about that in more detail. By the way, the upstream switch does continue to send them, though, so keep that in mind. Okay. So what's going to happen here is every switch is going to come online and assume it's the root. Okay? Like every child who's born into the earth thinks that they're in charge. You don't even have to teach them that. It's like, oh, I'm in charge here. And it takes a while to teach the child that, no, you're not in charge. Mom and dad are in charge. Same thing with the network. Okay, so every single switch thinks I'm the root. And if you do a show spanning tree at that point on the Cisco switch, or whatever the command is for whatever your favorite switch vendor is, if you're on that switch and you see it, it will say this bridge is the root. We assume we're the root to start with. But we do start to exchange what we call, it was just referenced, Bpdus. It stands for Bridge Protocol Data Units. Okay. And if you haven't heard of Bpdus, get ready, because you're going to hear about them a lot. Any spanning tree conversation is going to revolve heavily around Bpdus. And those who have been around a while are already nodding their heads and saying, yeah, we talk a lot about Bpdus. Sometimes often without really fully understanding them, myself included. So it helps to just drill in sometimes and try to learn what these are all about. This is what we'd call the control plane of the spanning tree environment. The control plane for any conversation is going to be around, whether it's routing or switching or anything, is going to be usually a layer of messaging that tells the switches and tells the routers and tells the networking devices how to behave at what we call the data layer, the data plane. So the data plane is the flow of actual traffic. The control plane is really just kind of negotiations. Like, hey, should this link be up, or should I send this traffic out that link or that link? That's what the control plane is. So these Bpdus are being sent out by the switches, and they're all sending them to each other. So we sort of have a collision of Bpdus. And what they're all saying is, I'm the root, and here's all my information. Okay? So how do we solve this first problem? The first problem being that everybody says that they're the root. Well, we're going to go through this comparison game and what we really call the root bridge election. Okay? Keep in mind, by the way, through this whole conversation, that switches are often called bridges, especially within spanning tree, hence the B here, bridge protocol data units. So just keep that in mind as a terminology perspective, that bridges and switches are the same thing. So we have, again, here's that keyword, a bridge ID. We all have a bridge ID. Every switch has a bridge ID, and the ID consists of two parameters. A priority, and then, big word, concatenated, which means it's combined with the MAC address. Which MAC address? Great question. Depends on the switch manufacturer. Usually there's a burned-in MAC address for the entire system. In the Cisco world, there's usually one per VLAN. It just depends on, and even Cisco is inconsistent. Sometimes they'll use the same MAC address for every VLAN. Sometimes they'll take a base MAC address and like add the VLAN ID to the end. So like, you know, the VLAN for 11 is 10 more. The MAC address is 10 more than the MAC address for VLAN 1. But either way, it's comparing the two. The reason why we use the MAC address is because it's supposed to be unique. So if we have a two switches talking to each other at the same priority level, which is a configurable parameter, then there's going to be a tiebreaker, which is the MAC address. One thing that we're going to learn in the world of networking is that there's a lot of instances where you have to memorize, is it the higher number or is it the lower number that wins? All right. Sometimes it's the higher number, sometimes it's the lower number. I will say this, usually, take this as a rule with exceptions, but I found this to be true more often than not. If it's a lower level protocol, meaning like layer 2, we talk about the OSI model, right? And so in the OSI model, we have the layers, and really 7, 6, and 5 are the application layers. 4 is the transport layer, 3 is routing, 2 here, this is where we're living with spanning tree. A lot of these tiebreaker scenarios are in layers 2 and 3 because we have routing situations, we have switching situations. In situations where we're comparing numbers, again, this will have exceptions, but just helps to have a starting point. Usually, if we're talking about a layer 3 protocol, the higher number will win an election, and if it's a layer 2 protocol, the lower number will win an election. Okay, I'll say it a third time. It's not the case every single time, but because spanning tree is in the realm of layer 2, we can think about that as being, okay, this is layer 2, this should be the lower number wins. And that's absolutely how spanning tree works. The lowest bridge ID will always be the root. Now, if we think about this concatenation concept, so let's say I have two switches talking to each other. Anybody know what the default priority number is, by the way, in a Cisco switch? Kind of curious if anybody out there is paying attention to or studying this already. And then we concatenate our MAC addresses. So let's say a MAC address ends with 01, and one of these MAC addresses ends with 02, and they're identical otherwise. So, I know my chat's a little bit delayed. I was looking to see if anybody's got that. Oh, there it is. Nate's got it. 32768. That's absolutely the case. Cisco, by the way, will only allow multiples of 4096, which sounds odd, but it will make sense later. We'll talk about that. Spoiler alert, it's because there's 4096 VLANs. But either way, 32, so it seems like an odd number, but it's actually very important. It's a binary, a power of 2. So this default priority is 32768. By the way, Bart, I just saw that you're in here, so hey, welcome. Nate, you were right. You were right. No need to second guess yourself on that one. 32768. So is the priority the same? Yes, especially if it hasn't been changed. Again, I can change the priority. The lowest number I can make it, by the way, is actually 0. I can make the priority 0. Best practice is not to use that. We usually want to start with 4096 as maybe the root bridge. If I want to force a switch to become root, I'd usually make it 4096, and then 4096 plus 4096 is 8192. So 8192 would be my next highest level, and that would be maybe my backup root bridge. This is coming from all of the switch installations I've done. It doesn't really, they're not going to ask you that on the CCNA. All they care about on the CCNA is, can you figure out which bridge would be the root? So they might actually ask us a question. They might give you all of the priorities and all of the MAC addresses, and say which of these bridges will be the root switch or the root bridge. So if my entire MAC address is a bunch of zeros followed by 01 and a bunch of zeros, or whatever it is, as long as it's the same, followed by 02, the lower of these two will be selected, which means it's this guy. Now, as soon as I change the priority always takes priority, so I would call it priority. So priority takes priority, which means that if I change that priority to be, let's say it's 4096 less, and I don't even know what that is, it's like 28,000 something. So if I make it 28,000 now, whatever that number is, 4096 times 7 is my guess, yeah. So that will be somewhere in the 28,000 range. Even though its MAC address is higher than the first switch, it will win because the priority is lower. Again, we think about this from a binary perspective. It's just a string of binary bits. That's all the bridge ID is. But that's important. This concatenation, the priority and MAC address, these come together, and we call this the bridge ID. Okay. We'll keep going. So we've got our bridge IDs. We're starting to compare them, and guess what's happening in the network? Some of these switches are starting to realize they're not actually the root. So let's just give these all different priorities. Let's say that, well, let's just say that they're all on the default priority, but this is our 01, this is our 02, and this is our 03. Okay, so because the MAC addresses are the exact same other than the last two digits, now we can look exclusively at these. So 01, 02, and 03. Let's see here. So what's going to happen is, as these guys talk right here, switch number 2, we'll call it, switches 1, 2, and 3. Switch number 2 is going to realize, oh, wait, I'm not the root, you're the root. And he's going to buy into this. Say, oh, okay, so you are the root. And switch 3 is going to say the same thing. Like, oh, okay, you're the root. And so I'm going to store that information. Now, the next step that happens is we start to pay attention to the ports themselves. Okay, when you are a root bridge, well, let me back up for a moment. There are 3 types of ports we need to worry about in a network from a spanning tree perspective. We have root ports, we have designated ports, designated, I'll just spell it all out. I was trying to think of how to abbreviate that. We'll just spell it out. So root ports, designated ports, and then we also have blocked ports. See, we have a question here. If you were to change the priority to create a new root switch on a live network, would it cause issues? Yes, that would cause major issues. Cause big time issues. If we were to change it, we'd go back into this concept of listening and learning, which we haven't talked about yet. But basically, as soon as I get a new root bridge in, I'm going to put all of my ports. It's called a topology change, and I'm going to put a lot of I'm going to put all of my ports into a like a listening and learning state. So basically, I'm going to shut all of my ports down for 30 seconds. So you just brought that network to its knees until the rest of the network caught up. Buffering issues. Huh. Yeah, I'm not sure how to fix that. Usually, yeah. Hopefully it's coming in all right for everybody here. So I'll have to look into that if that's on my end, or if that's universal, or if that's just on the download side. But is it actually is it freezing and then starting again, or is it lagging behind? Okay, Nate says no issues. So we'll just kind of push forward, and hopefully it buffers and catches up. Okay, so let's see here. Root designated blocked. So those are the port types. Okay. Next thought. Just my image freezing. Well, that actually could possibly be as long as hopefully the audio is coming through. All right then, because that could just be my webcam or something. Okay. So that was a good question. I believe that was from Nate. Yeah, that was definitely a good question. Okay, so every port in the network has to be identified as a root, as designated, or a blocked. So if we look at this scenario, like we just said, switches 2 and 3 realize, oh, hey, this is a root. You are the root. I'm going to call this a root port. Anytime we're going to map out spanning tree, we need to identify these ports. Designated port, by the way, well, let's start with the root port. The root port, every switch, other than the root, every switch has a root port, one root port. We're going to say 1 here. Okay? Every switch has one root port. It is the port that I know it's my fastest way to get to the root. If I have multiple ways to get to the root, we'll talk about that scenario here in a few moments, but basically I'm going to compare the Bpdus. Again, these Bpdus, they're kind of a big deal. My pen's backwards. There we go. Ooh, now I can put a star. So the Bpdus are kind of a big deal because they help me to understand not only where the root is, but hey, I've got 2 uplinks, right? I mean, if we look at this, switch 2 is eventually going to realize that the root is available this way as well, because it is. But it's also going to realize that, oh, it's actually a worse path. You know, if all 3 of these links are equal, we're going to realize that, hey, that's 2 hops away, and so that's worse. We'll get to those details here in a moment. So the root port, we've realized what the root ports are. What's the root switch going to do, by the way? Well, the root switch, every single port is a designated port on the root switch. So the temptation or the tendency could be that, oh, it's the root switch, therefore all of its ports are root ports. Well, they're ports on the root switch, but they're not root ports. They are designated ports. A designated port means that I am forwarding traffic out that interface. That's what a designated port means. Incidentally, I'm also forwarding traffic out the root port. And as you can imagine, a blocked port means I'm actually not forwarding traffic. So that's where those similarities end. So we're figuring out the designated ports. We're figuring out the root ports. This is, call it the easy part with our drawing. This is the tricky part right here. What is going to happen as we start to send each other Bpdus that say, hey, switch 1 is the root and I can get to the root? Well, what's going to happen here is there's going to be a comparison done. One of these switches is going to, I'll just write it out like this. One of these switches is going to say that this is a designated port, and one of these switches is going to say that this is a blocked port. Okay, now at this point, I don't know which one it's going to be. I just wanted to kind of show you that this is going to be the result eventually. So how do we decide this? Well, I keep using the word negotiation. There's really not a negotiation when it comes to spanning tree. It's more like throwing rocks at each other, and whoever's rock is bigger is going to crush the other rock. Okay, so when we're sending Bpdus at each other, one of those Bpdus will be what's called an inferior Bpdu. What that means is that I've got either a worse cost to the root, or I have a worse bridge ID. Okay, usually that's going to be the tiebreaker scenario or process. And we go through that process. We look at the cost to the root. First of all, we look at the root ID itself. We first of all need to agree on the root. All right, I mean, if switch 3 still thinks it's the root, well, then we've got some issues. Or not issues, but we have to start from there. We have to be like, oh, no, you do know that you are the root, right? Or that switch 1's the root. He learns switch 1 is the root, realizes that my best path is north, so I'll call it up, and now we're going to be back in the exact same scenario. So which root or which bridge ID is going to, or I'm sorry, which bridge is going to put their port into blocking? It's going to be the one with the inferior, again, the inferior port, or the inferior Bpdu. If I'm receiving, the rule is this, if I'm receiving a superior Bpdu, a better Bpdu, and it's not on a root port, then I'm going to block my port because they have a better path to the root than I do. Now, the order of operation for this is to first of all look at the cost. You know, I'm going to say, okay, switch number 2 says that I have a really good path to the root. Well, switch 3 is going to say the same thing. If those are both those links, those two links to the root are the same, I mean, it doesn't really matter which side blocks. So that's a tie. Okay, so that's good. Then we're going to look at the bridge ID itself. So my bridge ID, this is not the root bridge ID. I'll say this. This is my bridge ID. Okay. This is where we're going to end our tiebreaker process. Because if I look at this, switches 2 and 3, we already understand. I mean, there's not going to be a tie. One of those is going to lose, and we remember over here that it's the lower one that is going to win. The higher one loses. So at this point, switch 3 is like, I'm out. Okay? Your Bpdu is better. I'm going to stop sending my Bpdu out this link, and I'm just receiving Bpdus from you. And because of that, I'm just going to put my port into a blocked state. If a port is receiving an inferior Bpdu, it just ignores it. And that's true with any part of this process. Received inferior Bpdus are ignored because, again, think about that rock analogy or snowball or whatever you want to call it. If mine is bigger, I'm just going to keep throwing mine because it's bigger, and you can keep sending me that little guy, but you're going to lose. And usually, of course, that doesn't happen. It's, as soon as the inferior side gets the superior Bpdu, it's going to stop talking. So that's another key point in all of this. The Bpdu flow at this point is we have Bpdus flowing down from the root. They are not flowing back up. With traditional spanning tree, we do not send Bpdus back upstream. It's just a downstream conversation. All right, and then we have a Bpdu flowing this way as well. And just like we spoke about earlier, the blocking port means that it's not receiving those Bpdus, it's not processing those, it's ignoring those. Okay, so this is steady state operation in this network. We have root ports, both switches have a root port up to the root, and we have one side that has a designated port and one side that has a blocked port. By the way, thinking back 20 years, why does it matter? Like, why don't switches 2 and 3 just both block that link? Kind of curious what you think about that. Switch 3 is blocking all of the traffic coming from it. Why do we even bother sending broadcast traffic down towards switch 3 when we know it's going to get blocked? And another question, by the way, as you all type in there. There's a third tiebreaker here. What happens if the bridge IDs are tied? I want to know what situation would happen where my bridge ID is coming in and it's tied. I'm getting Bpdus in and like where those are actually tying. What's that situation look like? All right, so we got some responses in here. In case there's a failed link, in case the root goes down. So those are both good answers from the perspective heartbeat and recoverability. So good answers, but not quite the reason. Because, yeah, we do want that link to be available in case of the root going down, but if they're both blocking, we could bring that back up. The interesting scenario is this. Again, I dropped that hint in there. Think back 20 years. What do we have 20 years ago? We had hubs. And if there were hubs hanging off in here, we might have PCs hanging off of that link. Today, all of our switches are point-to-point, right? And so, yeah, to say that, this is in a blocked state, my brain, like probably everybody's brain in here, was thinking, so it's a dead-end path. It's a one-way street into a dead end. Why would we even do that? But no, actually, networks used to be built with hubs between switches. And so we had to be able to get broadcast traffic to those machines. And so if we think about it from that perspective, it makes a lot of sense why switch 2 would want to continue to send traffic, call it at switch 3, towards switch 3, but the reality is it's not for switch 3's sake. It's for anything that might live on that network segment. Okay. So as far as what happens if the bridge IDs are tied. So this is kind of an interesting one. why would the bridge IDs be tied? The only reason that could happen is if I have two connections between the same two switches. So if I have the same connections coming in, let me try. This drawing's getting really busy. If I have basically a second link in here, I'll just draw right over those arrows. There we go. Now we have two links. Now in this scenario, this is a bad example actually. This is a bad example because that'll just get blocked as well. The example would be this. What if I have a fourth switch hanging off of here? Doesn't really matter what the bridge ID is. We know as long as it's not the root. We know the root is up at the top. And so this switch is going to put both of its ports into a designated port state. Now this switch downstream, switch 4, call it, it's going to have to compare those two. And it's going to say, okay, well, both of these bridge port, or both of these ports, remember, this is trying to figure out the root port at this point. Both of these ports are trying to figure this out. And in the end, it says, oh, you know what? One of these ports is going to win out. So this is my root port, and this is going to be blocked. We would rather ether channel these if we bundle this together, then we wouldn't have to worry about spanning tree. But again, thinking what if situations plus spanning tree, I believe, came out before port channeling. And so we had to worry about this scenario. And at that point, we have something called a port ID. So the port ID is what's going to determine whether I block this port or that port. And by the way, it's the sending port ID. So I send a port ID down with every Bpdu, and the downstream interface is going to look at that and say, okay, which one is lower, because lower always wins, and that's my root port, and the other one I'm going to have to block. Okay. Highest port value number gets blocked. You got it, Alejandro. Yep. Very good. Hubba hubba. Thanks, Bart. Oh, okay. I'm not seeing any other thoughts or questions at this point, so jump back, again, shoot some questions into the chat if you've got any. Let's talk. I want to go through the from a blueprint perspective. When Cisco's talking about spanning tree, they want us to understand everything we've been talking about. Root bridge election is part of this. They also want us to understand a couple of spanning tree enhancements. In order to understand these, we need to walk through what the spanning tree process is from the switch's perspective. So when we connect I won't even say to connect two switches. When we bring a port online, this port comes up. In traditional spanning tree, what's going to happen, I say traditional spanning tree because we have some enhancements, but we have to understand, we have to have a starting point. So this is where we start, and then we can build some enhancements onto this. So if we have a port come online, the first thing we do is we go into what we call a listening state, usually abbreviated LIS. This listening state lasts for a set amount of time that I can configure. There we go. And I'm blanking. Is it the forwarding time, I believe? Whatever this time that I define is 15 seconds by default. And in the listening state, it's truly doing nothing other than sending Bpdus. But during this phase, this is when I'm doing all of these, we call it negotiations, but again, it's the rocks being thrown at each other. This is the phase when we are chucking rocks at each other. So we'll figure out whether I'm the root or somebody else is the root during the listening state. Then I go into the learning state for 15 seconds, or whatever I have set that to. So if I set that timer to be 5 seconds, then they'll both be 5 seconds. It's one timer shared between these two states. And at this point, I learn MAC addresses. I start paying attention. Where are all of these hosts that are out there? I understand now, probably maybe this is my root port. I've already figured all of that out, but now I've got MAC addresses coming in. I can start to learn where those MAC addresses are for 15 seconds. The way a switch learns a MAC address, by the way, is when a packet arrives. So every time we call it a frame really at the layer 2 level, but every time a frame or a packet arrives, I look at the source MAC address and say, oh, now I know where you live. You live out this port. If you're talking on this port, that means that that's how I get to you. So when somebody wants to talk back to you, I can send you out the appropriate interface. So that's how we learn MAC addresses. So listening and learning state total takes 30 seconds by default. And then I'm up. There was, anyways, my brain went somewhere else. So let's see here. We've got a question. We got a couple. All right. Do we have to configure these tiebreakers as it works? It just works. That's just how spanning tree works. Very, very thankful. We don't have to configure the tiebreaker scenario. We can, by the way, change bridge IDs because of the priority. We talked about that. You can also change the port IDs, the priority level of the port. You can't change the ID, but the port ID consists of a priority field and an ID field. And so that ID field is hard mapped, but we can't actually change the priority. So silly as it sounds, if I've got a switch like this and it blocks this interface and I want that interface to not be blocked, I could forcibly make that one by changing the that one blocked by changing the priority. So kind of a silly situation, but hey, we've got that capability. Another question from Corey. Despite being the root switch, does it send superior messages? Despite being the root switch. So the root switch will always be sending the superior messages. It's sending the best messages down possible because its priority is the lowest or its MAC address is the lowest. Because of that, it will always send its Bpdus out. If it gets an inferior Bpdu, it'll just ignore it. But I think Nate was the one who asked the question earlier, like what happens if a new root switch shows up, which can happen, especially if like you pull an old switch out of the lab. And this is why we can change priority values, by the way, because if everybody has the same priority, then the root switch on any given day could be different. If I plug a switch in, it's just a roll of the dice. Who has the lowest MAC address, the new switch or the old switch that was the root? So I've been, as a consultant, I've been in people's networks, and I found that closet switch out by the pool or whatever, that happens to be the root switch for the network. As you can imagine, that's not an optimally tuned network. When the switch furthest away from I was imagining like a high school where the pool room is far away. I don't that probably doesn't work with hospitals or maybe somebody's mansion has a pool room. I don't know, but I was thinking about a high school when I said that. So whatever switch is really far away could be the root, and that's not ideal. So I got off topic there, but to your question, I guess I want to make sure I understand that. Feel free to send a follow-up if I didn't understand that. But yes, it does continue to send its Bpdus down, which are the superior ones, until a new switch. That's how I got off topic. Until you connect a new switch, and then hey, everything changes. This concept of this listening and learning state, this is one of the reasons why we have to be careful with spanning tree, because if we do throw our network into a big hiccup like that, and all of these ports have to go back through listening and learning, then we're going to be down for 30 seconds, which in the 80s wasn't a big deal, but in today's network, the internet might as well have gone down if it was down for 30 seconds. So, all right, cool. Thanks, Corey, for the feedback. Okay. All right. Well, I'm not thinking of what I wanted to say. So, all right. So let's just kind of keep rolling here. So listening and learning state. So this is 30 seconds. There is another timer that is 20 seconds long that we oftentimes like to bring into this conversation. And it's like, okay, so I know for years I thought when you turn on a switch or you activate a port, it's going to take 50 seconds to show up. It does not take 50 seconds to light up. It only takes the 30, because that 20-second timer does something else that we'll talk about. But ultimately, this is the scenario. Now, Cisco wants us to hold up. We got another question here. I want to make sure we answer. Is this available to early 2000 cheap switches too? Explaining all my problems I had when setting up a LAN party. Yeah, you and me both setting up LAN parties in the late 90s, early 2000s, connecting all of our ports together for more bandwidth or what have you. A lot of those cheap bought from Best Buy type of switches, a lot of those did not get, a lot of those did not send Bpdus. So let me see here, Bpdu, spanning tree timers. So yeah, I wanted to talk about that. It's the max age timer. Okay. Well, anyways, we'll get to that. So yeah, that probably caused some problems. I did not mention it. So there are these 3 timers. Let's just talk about these timers for a moment. So the hello timer is 2 seconds. This is how often Bpdus are sent. And so you kind of get this pulse going through the network of Bpdus. Now, the weird thing is in the original spanning tree spec, even though everybody is called, everybody's supposed to send Bpdus every 2 seconds, technically only the root sends a Bpdu every 2 seconds. And my job as a switch is when I receive the Bpdu from the root, then I send my Bpdus downstream. So we're all kind of waiting for the root to send its messages. But in theory, we have this kind of, rolling out perpetual heartbeat that is initiated by the root. As we get into rapid spanning tree, we start to see that the Bpdus are sent every 2 seconds by everybody, and so that does sort of change. We mentioned already the forwarding delay timer. So this forwarding delay timer by default is 50 seconds, or 15 seconds, and that will apply to both listening and learning states. So we have to double it. If I set that to 5 seconds, it will take 10 seconds for a port to come online. And then we have that max age timer. Okay, so max age is basically, it's how long I time out or how long it takes to, well, let me hold up real quick. I need to make sure that I'm not insane on this. All right, so I'm kind of blanking on the max age timer because it's been a little while. What exactly does the max age timer do? Because I believe, we'll just worry about that. It'll probably come to me at some point. Oops, get rid of that. All right, so we'll talk about that later. I just feel like it's more about the maximum length of time that passes before a bridge port saves its configuration information. That's kind of weird. All right, so I apologize for that. I probably should have come prepared for that. Oops. So that's 20 seconds long. So we'll be sure to get a definition for that by the end of this. All right, so but this is where I thought it was 50 seconds because I took that max age timer into account. And we don't actually usually have to worry about that too much. I think what it is when I haven't received the root Bpdu for 20 seconds, then it's going to that's the max age timer. But that's what I was thinking. But I'm trying to find the validation for that. But oh well. Okay, so listening and learning. So we just talked about that when we're in those 2 different states. The learning state, I'm learning MAC addresses. And so once I'm up in 30 seconds, I'm up. So here's what Cisco wants us to know. There's this concept of something that they invented called Portfast. Okay, Portfast means that I skip listening and learning, which sounds a little dangerous, and it kind of is a little dangerous. But there's a reason we do it, and that's because we usually don't want to wait 30 seconds for a switch port to come online. So what happens when I configure Portfast, and why would I configure Portfast? Well, if I take a PC and I connect it in, why am I going through listening and learning on this PC port? There's no risk of a loop, and I need it to be online a little bit faster than 30 seconds. Think about it from the perspective of you go into a conference room, and so maybe even before wireless existed, or maybe the wireless signal is bad, and hey, this conference room has a port. So you plug the laptop in, and no network connection. For most of us, within 30 seconds, we're going to be like, this port's bad, and pull it out and plug it into another port. And so you think about that, that's not good. We need, when I plug it in, as silly as it sounds, we really need connectivity before 30 seconds is up. So what are we going to do about that? So Cisco came out with this idea of Portfast. Portfast is a specific, explicit configuration, and it's going to go onto that interface. And I will say spanning tree Portfast. Spanning dash tree Portfast. It skips the listening and learning state and brings it right up. So it just assumes that there's no ports, or no loops. It assumes there's no loops. It assumes that this is not going towards a switch. Because if it's going towards a switch, then it might, it might cause a loop. So this could be bad, because what happens if I can connect a Portfast interface to a switch? And let's say that we're already in this type of configuration, and I have Portfast enabled here. You know what's interesting is that when you configure Portfast on an interface, Cisco gives you a warning message. And it's phrased like this. It says, warning, this might cause temporary loops on the network. The reason why it's temporary, because by all rights, we just created a loop. Because it's temporary, or the reason it's temporary is because Cisco also has a failsafe. If a Portfast interface comes online, receives a Bpdu, it will go into the listening state and it will ignore the Portfast command. Okay, so Cisco was smart, and they said, okay, this could actually be a disaster because probably at some point we're going to connect a Portfast or switch to a Portfast port. This is going to happen, right? But fortunately it falls back. So the reason they say temporary loop is because how long did I say that it takes for Bpdus to come out? Like if this is the root and we're sending them every 2 seconds, so it might take 2 seconds and then boom, it sends it, and then boom, it sends it. So it might take about 2 seconds at the worst. Like if I just happened to it just sent the Bpdu and then I plugged in, it'll come right up and it'll be up for 2 seconds. And then the root sends its next Bpdu, it gets forwarded, and the switch says, whoa, 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 I'm out. I'm blocking this. I'm going into the listening state, which means it's in a blocking state. And so fortunately, Portfast has that failsafe. Okay, but obviously we don't want to do this scenario, but it is nice to know that Cisco's kind of got our back on this. So Portfast, the industry standard word for this is called a port type edge. This is called an edge port. So what we're going to find is, with tale as old as time, is Cisco comes out with an enhancement, and then the rest of the industry catches up. And so we progress from normal spanning tree, what we call 802.3d spanning tree, and then we progress to something called rapid spanning tree, which we'll still talk about. We've got half an hour left. Good. So rapid spanning tree is going to add a lot of enhancements, and one of which is the ability to configure this concept of port type edge. So now it's not just Cisco switches that have Portfast, because truly for a long time Cisco was the only one who could do this. You could almost call it and say that it was it's a reason to buy a Cisco switch over a competitor switch because we can do Portfast. Well, now everybody can do it, and rapid spanning tree kind of gets us spun up a lot faster in a lot of ways. But a lot of these concepts still apply. So let's, it's why we never want to jump right into rapid spanning tree. In fact, sometimes to a fault, because I will say this. I know when I was going after I got my CCNA, I sure understood normal spanning tree way better than I understood rapid spanning tree. Because a lot of times we end up spending all of our time talking about spanning tree, like traditional spanning tree, and then rapid we kind of ignore. We're just like, oh, it's faster. Are the timers faster in rapid? Actually not. They're the exact same. Rapid just works a different way. But most people assume, oh, it's rapid spanning tree. The timer, I know I did. For years I was like, oh, well, listening and learning states must happen in like 3 seconds. I mean, I can do that myself with spanning tree. It's not a good idea, to tweak the timers that much, but I could do it. That's not how rapid works. All right, so I'm getting ahead of myself. What was the other one? Thanks, Nate. I see that from the Cisco docs. The max age timer controls the maximum length of time that passes before bridge port saves its configuration Bpdu information, which is a really weird way of saying that. But I do think what that's saying is that if I don't get a Bpdu for 20 seconds, then I'm going to wipe out what I've pulled in. So, like I said, we'll get an answer for that here by the end of the night. So let's see here. We've talked about designated ports, blocked ports, root bridge, Portfast. Okay, Bpdu Guard. So this is the other one that Cisco. So I'm looking at the blueprint for CCNA for ICND2, and this is the other one that they have, is this concept of Bpdu Guard. So Cisco has a plethora. They have a lot of spanning tree enhancements, and this is just one of them. Bpdu Guard is an interface level configuration that says there should never be a switch out this interface, and if there is, I want you to shut down. Like, seriously, I want you to freak out and shut down if a Bpdu comes in. So it would basically be like saying, all right, remember this port? Let's make a blue switch, blue PC. So this PC is connected to the switch. There should never be a switch. Like, nobody should ever unplug this PC and then plug a switch in. So I might configure Bpdu Guard on that interface to protect it. In fact, Cisco even takes it a step further. They allow us to configure Bpdu Guard by default on non-trunking interfaces. So you can make that a global configuration for a switch. And I dare say it's best practice. I mean, if you're able to do it, or if you are comfortable with that configuration, you understand the implications of it, then you can do it. Worst case scenario is you're going to have somebody call you one day and say, hey, I'm plugging the switch in like you told me to, and it's not coming up. And you're going to be like, oh, right. Yeah, because by default, Bpdu Guard is enabled. So, it's just one of those things that you have to remember down the road as far as why something's not coming up. Bpdu Guard, if a switch receives a Bpdu, so let's say a Bpdu comes in from this interface. Maybe, by the way, don't forget my horror story. Yes, all right, I'll tell you my horror story. If that Bpdu comes in, and maybe that's a malicious hacker. Maybe that's somebody who's trying to take over, by the way, your spanning tree network. Can you imagine that? Somebody's like, hey, I'm the root bridge. That would actually be pretty bad. So Bpdu Guard helps with this. I just received a Bpdu on this interface, and boom, I go into what we call the error disable state. So some of us have probably heard of this. If you have any experience with error disable, good and bad news of error disable. Error disable means that it's truly shut down and there's no traffic. That's the good news. The bad news is the same thing. It's shut down. You can't receive any traffic. This isn't the horror story I was going to share, but there's another horror story. So I was at an install, and this doesn't have anything to do with spanning tree. Error disable is a state that a lot of different situations can put a port into error disable. One of which is if the link starts to flap up and down. Well, to protect the switch from all of this spanning tree, so it is related a little bit, but to prevent the switch from having to deal with spanning tree stuff up and down and sending traffic and not sending traffic, if a link flaps too much, it'll put that port in error disable. The only way, by default, to get a port out of error disable is to shut and no-shut that. Well, we were bringing a switch online from a site like 20 minutes away, and guess what? As we were bringing that up, I don't know if I just, plugged the fiber in a little too wonky or what, but the switch on the other side put that port into error disable, and we had to drive. Fortunately, it was only 20 minutes. It could have been a lot worse, but we actually had to drive to that site, and the customer, this is like a government agency, they were like, just a local government agency, nothing too Fort Knoxy here. But he was just like, we couldn't figure out how to get into this building, and then we couldn't figure out how to get to the switch. And, it cost us like 2 or 3 hours just because that switch decided to go into error disable. Here's the good news about error disable. There is a configuration called error disable recovery. Every single one of your switch configurations should have error disable recovery as the word's escaping me. Policy, that's it. You should have a policy defined. If you or your network admin, whoever's in charge, says our policy is it stays off no matter what, then that's at least a policy. But in a lot of cases, it's best just to say, you know what, error disable recovery, and you can set it up to like 60 seconds. And so after 60 seconds, it'll try again. It'll bring that port up, and if it's still flapping, if I get another Bpdu, I'll shut it back down. And worst case scenario is it's going up and down and up and down. But guess what? I mean, if you're paying attention to, if you've got a network monitoring service, and you get that, you get that alert, then at least you know that there's a problem out there. And you can see a little more information that way. So I always, my default switch configurations always had error disable recovery in there. Every type of error disable has its own enablement, so you can enable or disable it. The timer is global, so you'd have to say it's always 60 seconds. But then you can say if it's flapping, just keep it off. But again, for the most part, you're going to save yourself time by enabling that error disable recovery. All right, so that was a little bit of a tangent, but again, that's a real life situation. Northern Hurricane 7. Yo, Jeff. All right. Yo, Northern Hurricane 7. Probably know who you are, but not by the name Northern Hurricane 7. So sorry about that. All right. All right, so let's see here. Let's take a look at the blueprint here. So there are, by the way, a lot of other enhancements. We have Loop Guard as one. We have UDLD. We have a couple of other things that Cisco might want us to know for higher level exams, but for CCNA, this is really good. All right. I guess the next thing I do want to talk about is per VLAN spanning tree. So let's go ahead and do that. There's a lot to cover in spanning tree, I tell you what. I think I almost wanted to do this with another topic. We'll be lucky to be done here in 20 minutes, but done we shall be. All right, so Cisco saw this situation where when we take normal spanning tree and we get a blocked port, how much traffic is going across that port? In theory, 0, right? I mean, if this is the root port, the root bridge, then well, it's probably not the root because you almost never are blocking a root port. You aren't. Well, anyways, either way, it could be. It doesn't matter. Sorry, I'm getting complicated. So either way, we're seeing some Bpdus, but I mean, there's no traffic. We're by all rights, we are wasting that link. Okay, now, back in the day, and even today, if this is a 10 gig link, will you be happy that that's blocked? I mean, back then it was a 10 meg link or a 100 meg link. Like, man, I paid all this money for a 100 meg link and it's getting blocked. Well, in today's terms, what if that's a 10 gig link? Would you really want a 10 gig link being blocked? I mean, those optics are expensive. If those are optics, you might have paid $1,000 for each one of those optics. And so, yeah, I mean, we don't want the 10 gig link being blocked, but we do have to have it blocked. So how do I utilize that link while also keeping my network safe? Well, Cisco came up with a pretty clever solution, and that's to say, you know what? Every spanning tree topology really is only significant from a broadcast domain perspective, which makes sense, right? I mean, if I send broadcasts out, I need to block those broadcasts from going all the way around in the loop. But I do have multiple broadcast domains in the network, and we call those VLANs. So if I have 10 VLANs in the network, I could probably have 10 different spanning tree topologies, or at least 2. And so let's make a different blocked link. We'll make this one blue, purple, whatever that color that is. And so for VLAN purple, let's say this is VLAN 10, let's say pink is VLAN 20. So for VLAN 10, excuse me, VLAN 10's loop kind of looks like this, right? And this link is dead in the water. It's another 10 gig link, but now with VLAN 20 in the mix, its loop goes around like this. So now VLAN 20 is using the 10 gig port interfaces link on the left. There we go, I got it out. And VLAN 10 is using the interface and the link on the right. So this was Cisco's idea, was to make it a per VLAN spanning tree, and that's actually what they call it, is per VLAN. PVST, per VLAN spanning tree. Okay, so Cisco wants us to understand that this is where, this is the base level for a Cisco switch. In fact, if you pull a switch out of the box today and turn it on, if it's a catalyst switch, it'll by default start running per VLAN spanning tree. Technically, it's PVST plus, and they just added some enhancements at some point, so they took PVST and added PVST plus. I think it has to do with the VLAN count or something like that. I looked it up once, and it wasn't interesting enough to remember what the difference was. So PVST plus is how Cisco does spanning tree. And so if you enable rapid spanning tree, technically what you're enabling is rapid dash PVST plus even, I think. I don't know, but rapid PVST. So Cisco's protocols are for this. Now, the good news is I can utilize all of the links in my network, and I can utilize them well. If my 10 gig link were to, let's say it the other way. The normal spanning tree, the non-Cisco version is called, we'll write it up here, Common Spanning Tree, CST is what it's called. The industry eventually came out and has now come out with something called Multi-Instance Spanning Tree, or MST. So the green ones there are Cisco, and the red and blue ones, the purple ones, those are the industry perspective. So the good and bad of PVST is that, hey, I can do exactly what I just drew out there. Generally speaking, we only need 2 topologies. And so even though I've got, if I have 2 VLANs, I've got 2 topologies, which is great. What PVST kind of does as an accidental side effect is if I have 100 VLANs, I now have 100 VLAN instances. Or I'm sorry, I have 100 spanning tree topologies. Every single route is elected individually based on VLAN. Every single Bpdu is sent individually based on VLAN. So everything we've talked about up until now, if I have 20 VLANs, that is 20 route bridges. Might all be the same physical switch, but 20 individual route bridge elections, 20 Bpdus sent out every 2 seconds. And, is this a big deal? Not really. Modern switches can handle this, no problem. Multi-instance spanning tree, which is not on the CCNA, at least as best that I saw. I don't believe it is. Multi-instance spanning tree tries to solve that problem by basically saying, okay, rather than doing a spanning tree instance per VLAN, we'll do a spanning tree instance per what we call, it's truly called an instance. You define the instances, like purple and pink here in my drawing. I define my 2 instances, and then I assign VLANs to each instance. And that way the switches are sending Bpdus only for the instances as opposed to each individual VLAN. So it actually cleans it up a lot better. On paper it's a lot better, but because it's more complicated and it doesn't really solve a problem, it on paper again it looks bad to say I'm going to do this 20 times or 100 times, but because the switches can handle it and because there's no real issue with it, a lot of networks, most networks that I know of, just default to rapid PVST. So we're not really having to solve that problem. The big thing with rapid, so let's go and talk about rapid spanning tree. Rapid spanning tree, as you can imagine, speeds things up. We don't like sitting there for 30 seconds listening and learning. We don't like the idea of I think that's really the biggest thing. Well, no, I shouldn't say that. We already mentioned it earlier. This waterfall cascading style of Bpdus, we kind of want to get rid of that. We want to be able to talk to each other so that we understand when something goes wrong. So that can be a concern. So rapid truly makes it into a negotiation type of protocol. A lot, like I said, my misunderstanding of rapid was simply that the timers are lower. But again, we can lower the timers in normal spanning tree. So out of the box, Cisco's going to, if we turn on a catalyst switch, it's going to be running normal spanning tree, PVST. I can enable rapid and I can enable MST. I can be running in one of these three operations, but my entire network really needs to be running the same thing, or there's going to be some problems. Rapid PVST is rapid spanning tree. This is getting to my horror story, by the way. So, Corey, hopefully you're still on the line, because I'm getting there. Rapid PVST is backwards compatible with PVST. But I will say this is what happened to me. Okay, so let's just pull up another drawing here. This is my horror story. This is fun. So I worked for a large medical clinic for about 2 years, and it was like 7,000 staff, 700 doctors. It's pretty sizable. It's a pretty sizable medical clinic. And our second largest site, and I couldn't tell you how many people were there. We just needed a switch replaced, I think. It might have even been just a new switch installed, but I think it was replaced. And so I went out there during the day, and oh, okay, Jack, you gotta take off. That's fine, thanks. We were just to be clear, up until now we've always been doing this for an hour. The Twitch streaming I was planning on doing until 9:30. So if anybody else needs to get going, that's good. 9:30 my time. But I'm planning to go until 9:30 or so. All right, so here's the situation. We had 2 older core switches, and these were running PVST. And then we had this switch down here. Now the plan was to update this to rapid. We wanted to get this to rapid eventually. These were old. If I remember right, they were actually Catalyst 4006s, maybe. They were on the older side. And so this switch needed to be connected up. Oh, you know what? I remember what it is. This was the topology. I wasn't swapping the switch out. I was going to link this connection up. That was why I went out there. The interesting thing is that this switch right here was running rapid spanning tree. Now, this wasn't causing a problem. At this point, there's no loop, so there shouldn't be a problem. But it also should just work. To connect, my goal here, of course, as you can tell, is to get this second link up. Because for whatever reason, this switch had been installed, single homed. We really wanted it to be dual homed. So I went out there, brought my optic, connected it, and plugged it in. And that's when all heck broke loose. So really what happened here was somehow these 2 switches did not see each other from a spanning tree perspective. So neither put their Bpdus into neither put their ports into a blocking state. And because of that, we had this big loop, and within, I kid you not, I think within about 30 seconds, the network was on its knees. And so, fortunately, I realized it pretty quickly. I was able to unplug it. Wasn't too bad. I did get chewed out a little bit, only because I was doing it during the day, but my argument was, it's supposed to work. We do this all the time, kind of thing. And so, in the end, literally, I went back out there in the middle of the night and plugged it back in, and this time it worked. So there was no configuration error. There was nothing going on there. It just didn't take. I don't know. It was something to do with the fact that this was running PVST and this was running rapid. So cautionary tale. They are supposed to work, and in the end, it did work for me. But messing with that during the day on a live network was maybe not the right answer. I was probably about 4 years into the industry at that point, and did not stop and think that maybe something might go wrong. So that's my horror story with spanning tree. Just keep in mind that the compatibilities that they're supposed to be compatible, just because it says that doesn't mean it necessarily is. All right, Nate asks, what rapid spanning tree is different than Portfast, right? Okay, it is different than Portfast. However, it is when Portfast was introduced into the industry standard vernacular. So when the rest of the world, when rapid spanning tree was developed as a standard, and Cisco, of course, used that to build rapid PVST, this concept of rapid spanning tree had Portfast. They don't call it Portfast. Portfast was Cisco's word. I mentioned a couple of enhancements that we don't need to worry about for the Cisco exam. One of them is One of them is called uplink fast. One of them is called backbone fast. And then our favorite, which is Portfast. So we start to see the similarities here. Oops, I didn't even write fast. There we go, backbone fast. So Portfast, uplink fast, and backbone fast are all Cisco enhancements on Cisco switches that enhanced spanning tree, and in some cases prevented loops when there were some, call it some failures to understand what might happen. And that's what uplink. That's a lot of what backbone fast does. So they're all intended to get you back online and running as fast as possible in the event that there's an indirect failure and things like that. So Portfast, of course, gets you online faster. All of these enhancements were added into the rapid spanning tree spec. Cisco never abandoned the Portfast verbiage, so kind of yes and kind of no. So a catalyst switch, it's still spanning tree Portfast. Even though it's really a edge port. Any other switch out there is probably going to be edge port. Incidentally, does anybody use Nexus switches out there? Kind of curious. If you do, chime in, let me know. Nexus switches are fun because, they're data center switches, but they're also, I call them the new modern switches. They came out in 2008, so they're already 11 years old. I don't know why I looked at the calendar to see. I feel like I should know it's 2019 at this point. So, Nexus switches sometimes will do they like to abandon the Cisco verbiage. And so they don't call it ether channel anymore, which is a Cisco word. They call them port channels on the Nexus. Kind of interesting, right? Why would they do that? I have no idea. They just wanted to embrace that. Well, the most obnoxious version of that is when instead of getting onto your interface and typing in, spanning tree Portfast, you have to type in spanning -tree port, that's space port space type. I'm behind the camera now, aren't I? Port type edge. That is the command to enable Portfast on a Nexus switch. So Nate, you're on the right track because it's part of the spec and it's part of spanning tree, but from a Cisco perspective, it's really not, because Cisco had it before Rapid and they have it after Rapid, and it's the same command to enable it either way, and under the hood is doing the exact same thing. So, but the rest of the world was able to start doing this when Rapid Spanning Tree came out. So Rapid Spanning Tree, believe it or not, there's not a whole lot to talk about with Rapid Spanning Tree. There's a few things to keep in mind. Let me go back to this. Yeah, we'll keep this. So first of all, when I block a port, let's just say this is my blocked port. Oh, whoops. Wrong layer. There we go. So let's say this is my blocked port here, the red one now. In a normal spanning tree environment, these Bpdus continue to send down, but I better double check this. I believe that it goes up like this. That they're talking to each other even with a blocked port. I know that they continue to talk to one another. Let me see here. That might be another Cisco enhancement that I'm thinking of. All right, I'm gonna have to come back with some information for you guys next week. So I apologize that I'm dropping the ball on some of this. What the key with Rapid Spanning Tree, and all you really need to know, is that all of these timers continue to apply. We still have listening. We still have learning. We still have forward delay. So that forward delay of 15 seconds can apply. Oh, you know what? Yeah, there's a couple of key differences. First of all, Cisco, the industry renamed these. Okay, so we don't have blocking anymore. We have discarding. We have forwarding, discarding, and learning. So they got rid of listening. I don't know why, but they did. So you have 15 seconds of discarding because it's the same process. 15 seconds of learning, but it's the same. Again, it's the same process. At that point, it enters into. It's gonna bring it up just like usual. Okay, so that's 30 seconds. How do we avoid the 30 seconds? Well, Rapid will do something cool, which is that when I send my Bpdu, I can actually send a response to that and have a quick handshake, which is to say, oh, I think I should be blocking. What do you think? And if he says, yes, you should be blocking, I should be up, boom, we're done. We figured it out. Why do we continue to do it? Or vice versa, like, hey, I think this. Oh, yeah, I agree. So it's a quick handshake. It's a quick negotiation. Some parameters are handed off, compared in the Bpdus, and it's triggered by, I received a Bpdu, I'm going to send you one. Okay. The other thing is that all switches send Bpdus on their own 2-second timers, so we're not waiting for the root anymore. And that's just in case the root goes down, we can kind of figure things out a little bit faster as to what's going on. But that's about it with Rapid. The majority of what we need to know and understand with spanning tree is everything we've talked about tonight, because if we don't understand all of that, Rapid's not going to do anything for us. I mean, like, again, a lot of the underlying concepts are the exact same. We just have to understand, blocking becomes discarding. Everybody still calls it blocking. Everybody under the sun calls it blocking. But, hey, it's a different verbiage. But it's really about that negotiation point. That's what gets us up faster. And so when we have Rapid enabled and we plug in 2 switches, we'll see that comes up a whole lot faster than 30 seconds if Rapid Spanning Tree is enabled. So it's good timing. We're about 3 seconds short, or 3 minutes rather. We're coming up on our time here. I'm going to bring a little bit more information next week. I'm going to make sure that you are well educated on the max age timer. I'll double check the Bpdu directions there, just because I want to make sure that we're all squared away on this before we dive into the next section. By the way, the next section next week will be the other half of this. I think I just actually, you all have the schedule up in front of you. I don't. I believe it's just called Lan Switching, right? So Lan Switching it's basically everything else. So if you pull up the document, in fact, here, let me just do this. So everybody can see this all right? Is that right? Yeah, looks good. So this is the blueprint for the CCNA ICND2. So we're in Lan Switching right now. This is the 1.0 section. And really we covered just these sections right here. So you can see that we talked about PVST plus and Rapid. We talked about the root bridge selection, which is very complicated for just being one little sub-bullet point. We talked about Portfast. We talked about Bpdu Guard. So next time we'll finish up on spanning tree. Anything, if you have any questions, feel free to post them in the Twitch chat or hit me up on Twitter at Kish2 to let me know that any questions that we need to answer. I'll come in and kind of talk about a few of those things, and then from there we'll talk a little bit about VLAN and switching. I know DTP is probably something we tend not to use a whole lot. VTP is going to be something that we use a little bit more. We definitely need to know it too. And then also ether channels and probably a little bit of the security threat mitigation techniques as well. So that's that. Okay, thank you, Gus, for confirming it's Lan Switching. So I see some of y'all are signing off, so I think I'm going to do the same. So thank you very much. Appreciate everybody coming out. It was a lot of fun, and we'll do it again next week if you can make it. So have a great night, everyone.